So today I'll be talking about high-level synthesis and explaining more about it as we go through an example of finding a running average of 8 numbers. So here's the idea of high-level synthesis. The options that we get from high-level synthesis is we can use the PDL language or the C or the system C. So you have a wide variety of languages with which you can compile your code in and then get the RTL. So as you know, high-level synthesis basically converts your C code to your Verilog code, C or any other code of your choice, and basically it does a few processes which I'll be going through in detail, and then it produces the Verilog code with which you can do further simulations. So let's start off with the simple code of running average of 8. So before that, let me just show you the options that I was talking about. So if I go here and project option, as you can see, this is what you get when you open your project, and you have your language for PDL and the system C and the C or C++. So this is your language, and since I'm using D1 Terasic D1 SoC board, which is a Cyclone 5 chip, so it has 50 megahertz of oscillator on the board. So I'm gonna be my target frequency would be 50 megahertz. So as you can see, for 50 megahertz, we are representing in terms of 1 by 100 nanoseconds to be more accurate. And there's some clock uncertainty it takes into account, which it'll come into use later, and the effective clock period. And this is our board, and let me go ahead and redo this, or yeah, anyway, this is my board, and 31. And then you have the logic synthesis tool of quarters, which I've already you know uh, sourced it into my bash file, so I can directly call quarters into this CWB. And then I have the libraries here. So here is the basic library, BLib library, which, as you know, these library contains the values of power, delay, and other information of important gates. So BLib basically contains the information of basic gates, and FLib contains the information of more advanced gates, like uh, different bit sizes of adders. So it basically has values of those blocks. Mux is whatever you can think of the other blocks other than the basic block. So that will be contained in FLib, and this will have the basic blocks. So having done that, click on apply and you continue ahead. Okay, so here is our C code, simple C code. If def C, if def C is basically an indicator to our GCC compiler saying this should be read as C. So that is what is being done here, and this ends here. This is basically library general library definition, and here we have the buffer which shows the 8 values. Then this basically tells the cyber workbench that this is my processor, this is my main module. So average of 8 and 0, it is the input, and this is the output, and this is the sum. So what do you do? You basically uh, shift the values so that you can shift the values towards your left, so that you can add the new value that you want into the buffer 0, or towards your right, and then you find the sum of that buffer, and then you divide it by 8 to get the sum. So this is how you get the running average of 8 numbers. And then we have the test bench for the same written in ANSYS. See, again, this is a directive for GCC to tell us that this is a C code, and here we have file FPI. These are file pointers for input and output. As you can see, file pointer input, it opens the in data text, and then we have the file pointer output, which points towards the out data text. And here this for loop is basically for scanning the values of fscan or file scan of pointer pointing to I, and it basically it takes the value from that file until the end of the page, and then it breaks out, and that value is sent into this module of average. or this block of average 8 functionality, and then the output is sent here, and that output is saved into this this file. So basically, yeah, that is what is going on here. And having said that, now let's move on. Let's see, look at, as we have many options here. Now let's go ahead. The first step in HLS is to parse your code to check for syntax errors, anything else you could think of. So that's what you start with. So this parsing is your first step in HLS. So yeah, having done that, if you're good enough, then it should show this that it's done. And then what you do is, then we go, if you're done with that, then you get this blue folder. Now in this blue folder you have a lot of options where you synthesize, generate constraints, and all this. So let me talk about HLS. HLS is basically, it needs three inputs. One is your C code, next is your target frequency, and the other thing is your functional constraints and your libraries. So yeah, as I said, initially I got the libraries when I sent it through when I was defining my project module. I also gave my libraries, the flib and the plib, and then we have my C code, and I also mentioned my target frequency as 50 megahertz within as I was defining my project. So what do we need then? The missing content would be your functional constraints, basically the amount of blocks that would be needed to satisfy your functionality, the functionality you are trying to achieve. So yeah, to calculate that or to understand that, we can go here and we can say generate flibs slash fcount, and you can see there are many options here. This generate library for basic operators, and generated file is flib or fcount. So yeah, there are many options here, and you can also set a limit for how many of the functional blocks it could use at a time. So I'll be setting as 10 here and give generate. So for this functionality, as I give generate, I get this fcount module as a constraint result. As you can see, it says it needs 4 8-bit adders and 3 12-bit adders, unsigned. Both are unsigned adders. So this is what it needs to realize this functionality within the given target frequency. So yeah, having said that, now we have all that we need to do the synthesis. So again, let's go over and look at few of the options that we have if you want to do synthesis. So here are the three modes of synthesis options that we have. Manual scheduling, where you can schedule each blocks independently, or you can divide your program into blocks so that each block can be executed within the time period of frame that you would want to execute it in. And then we have the automatic scheduling, where the cyber workbench in itself does the scheduling for you, fully automatic. And then there is the pipeline scheduling, which is another good option that CWB provides. So yeah, having said that, mine would be in automatic scheduling, and once you click execute, this is a control flow diagram. uh, Back, as you can see, this basically represents the flow, the date, what are the blocks being used, and the flow of data flow of our functionality of running average of 8 numbers. So as you can see, we have the buffers here, and during the reset phase, all the sequential circuits, or basically any circuits you want, it starts from reset. Basically it clears all the buffers here, and then after that, as it enters its first state, as you can see, the buffers are loaded with values. As you remember, for calculating the average of 8, running average of 8, you always shift the values and add it to the buffer. So that is why you got the buffers here, and then we got the adders here, which basically does, as I said, there are 4 8-bit adders and 3 12-bit adders that are being used here. And this basically represents the flow of how the program goes on. As you can see, if it reaches init, and this functionality will be done over and over again. And here you have the sum, you have the out 0 that we actually showed initially, and then we have the output, and once you're done, it shows the end. So this is the flow, general flow of it. Right then, so our synthesis done successfully. So what this does is, this PDL tran basically does allocation, scheduling, and binding. So allocation basically refers to, how many blocks you need to, to realize your functionality. That is allocation of blocks that you need. And functionality, I mean, scheduling is basically how you schedule those blocks within the given time frame. Since I've given it as 50 megahertz, as you can see, the clock period would be 20 nanoseconds, and to realize that functionality you need only 2.054 nanoseconds. So yeah, we can have our whole block in within one cycle. So that's why we have a latency of 1. And then we have the binding, where each of the blocks are given a certain, or whatever the functionality you needed is being mapped onto the blocks. So that is what this whole step of synthesis does. It basically takes the C code, parses it, and then it does these three main steps of allocation, scheduling, and binding. So, as I was saying, now let's continue to look at more options that we got here. So as you can see, this is the QR report, or the cyber synthesis report, that you get from your initial simulation. As you can see, this also gives out an estimate of ALUTs being used and the registers, clock period, critical path. So this gives a rough estimate here. This definitely is not the absolute, because it only it doesn't do the routing, it just calculates based on the cell delay that is given in the libraries. So yeah, it is not very accurate, but it provides a good ballpark. And this also ALUTs and registers, it's all a big guesswork. So here we can see how the functional units are being used, and within those, how this adder and what it contains, the functional unit each of which. And then we have the register data and the multiplexer being used, memory, and the latency. As I said, since our whole functionality could be fit within our target frequency, there is only a single latency. There is one single state machine, because you don't your functionality is done within the same clock period. And then we have the path here, the longest path, the delay, the critical path. And yeah, so we have the nets and the other stuff being mentioned here. Now let us go ahead and look at some more options that is provided here. We have the signal table, the data path, synthesis graph. So let's look at the data path here. When you open your data path, you get how your blocks are being arranged here. As you can see, all the data. This usually shows FSM too, but here it's not showing FSM, because, as I said again, everything is being scheduled within one cycle. So yeah, you wouldn't need more than one state machine, or there are no state machines to go further. As you can see, we have the functional units, the 12-bit unsigned adder, the three 12-bit unsigned adders here, and the four 8-bit unsigned adders. Now you can also view the critical path here. As you can see, the critical path that you saw, you can see it here being marked. So yeah, this red line shows you how the critical path moves around. And you can always go back to your C code and look at the same. So yeah, that is one of the things. Yeah, as you can see, every time I press it basically maps onto your C code to see what is going on. So moving on, we also have some other things that we want to look at. So here is a signal table. As you can see, this basically, as you can guess from the name, it shows all the signals that we need and the type of signals that they are, read and write. So yeah, that's what it shows. And you can see it shows also the bit width of each of this. So yeah, that is your signal flow, or the signal table graph. Now having done that, you already have your Verilog file here. See, as you can see, it generates the Verilog file here based on your C code. And yeah, this is why we use HLS. Now there's also another option where you can compare. Yes, let me go ahead and show this to you. So here is your design vision, and this basically shows. So yeah, let me just go back to that again. So yeah, as you can see, we have the LUTs and the latency cycles here, latency index. You can see I have used the latency index. This basically is a graph to plot. Each point shows every time you hit the synthesis button what's going on. So you got the options of checking. See, for the first time I hit synthesis, 69 ALUTs were being used and the latency was 1. And then the second time I hit the synthesis button with varying conditions, I got 93 ALUTs with, you know, different latency cycles here. So that is what is being shown here. Again, we can always compare it with other stuff. As you can see, the register, the DSP being used. Since we are not using DSPs, it doesn't come into play here. Or as you can see, then yeah. So this is what you get when you open design vision. So you could see how your design has progressed with varying conditions. Now, as I forgot to talk about this. You can always go here and change the number of functional units that you would want to use. You can always have a restriction, or you can give some. It doesn't matter if you give some more, because I've already given it the limit of 10 and 10, but still it decided to use 4 and 3. So yeah, there's no point in increasing, going beyond this whatever limit. But again, you can always reduce it, and having reduced it, you can always change it to manual, so that the when you're doing synthesis, the PDL-TRAN uses only your FU constraint. So yeah, let me just go ahead and resynthesize this. Again, you can see I get this graph. Now, having said this, now let's move on to the logic synthesis part. Now, for the logic synthesis, you have your Verilog code. Now you got to perform your logic synthesis to do the mapping to the cells. So that's why we use the logic synthesis CUI. As you can see, it calls on the quarters from which I have sourced from externally. So yeah, it basically runs quarters within, which makes it so much more easier. And then as it runs, I'll just go ahead and explain a few of the other things that we can do. As you can see, we are using quarters for logic synthesis. When you do that successfully, you get this file with all these options, and just like in quarters, you get all these summaries of reports and summaries of everything that you could see, even the timing and pretty much everything. See, you can also have the timing here, which is being defined according to the project settings that I had initially put out. So yeah, you can see the fitting summary of 25 ALN. Of course, these numbers are going to be more or less because this does more accurate calculation according to our FPGA needs, and that basically it is a rough estimate of the things. So yeah, this is what you can. Now you have performed your logic synthesis, you can go on and do your simulations now. So yeah, we can always start with software simulations here. So let us let's look at the options that we have in simulations. When we go here, as you can see, we have the behavioral, C++, cycle, bit accurate, and a whole bunch of other options that we could use. And here, basically what I've done is, I've done my software simulation, with which I just gave my input file and built my system, and then I got this output text for my given input data. As you can see, just to make sure, for the average of 2, 5, and 7, I got it as 1. So yeah, for every input it calculates your average. So that's what is being done here. Now, having said that, if you're done with this, with your software, the software basically checks your functionality of the circuit if it's functioning properly. So yeah, It doesn't take timing or any other factors into consideration. It just checks the functionality with respect to inputs and outputs. Now you can always do your RTL simulation here. As you can see, I can go ahead when you click at this, and when you click at RTL, you get RTL and RTL only. So yeah, you can always do your RTL simulation. Let me just go ahead and show a few of the options that are here. As you can see, every time you open that, you get a whole lot of settings where you can use a bunch of simulators here, but I'll be using model sim, and these are some of the options. And the right, this is an interesting option. This is a very interesting option where the input will be sent continuously when you click every cycle. So for every cycle, the input will be sent to the module, even if the module is ready or not. So that doesn't help usually. So we also have what is every valid cycle. So yeah, this is basically like a handshake mechanism that when an output is ready, it basically asks for the, it sends out a signal saying that I'm ready to take an input, and that's when the module sends, you know, the input values to check. So yeah, this is basically a handshake type thing being done for more accurate simulations. You also have more from the pattern files, or it can use some random data. And yeah, even the radix, you could always adjust your radix here. And yeah, so that is one, those are a bunch of options. So what you do is initially you take your RTL, you get it done, and then you add your files here. These are simulation files which you need. So instead this, when you're doing simulations, RTL simulations, you need it as .clv files and you can't use text files. So yeah, you got to make it into .clv file, clock level simulation. And yeah, and once you run this, you should see it generates a VCD file which you could always use, you know, to dump it onto any other VCD dumper and check the waveform. And but you can always compare the outputs. As you can see, we have the outputs here for the given data. Here is the out data that we'd expected from the software simulation, and as you can see, it's matched here. This doesn't happen usually. The last value gets truncated when we're doing RTL simulation because of the latency. The the last calculation will still be going on, and just as it gets it to the last value, it truncates. So yeah, it doesn't get time for the processing to be done for the last data. So what we do is I usually add a 0 towards the end, and that's when you get the proper output data. So yeah, these are some of the options that you can do. And yeah, this is your introduction to HLS using a simple average 8 calculator, a running average 8 calculator. Thank you.